Oh, right. Okay.
Hi, Steve. How are you?
Hi. Very good.
Long time.
Yeah. Where are you now?
I'm in Stockholm
Oh,
right now.
okay.
Yeah.
For how long? Since when?
This is already my second year, and I will finish in November.
Oh, okay. Right. So how's it gone? Has it been a good time?
Yeah, I would say also now the weather is better. So before, actually, in the last 3 months, I was not here, so I came back just yesterday.
Okay.
So I escaped from the winter.
Right.
It's it's crazily raining here in Portsmouth. It was
Actually,
clear sky in the morning, and now it's raining, fully raining.
mhm.
Yeah.
Well, get used to UK weather.
Exactly. Actually, I think that's quite common in the UK. Actually, it's sunny in the morning, then rainy in the afternoon,
Mm.
or rainy in the morning and rainy in the afternoon.
At least half day.
Exactly. At least half a day, possibly the whole day.
But generically, I expect that UK is quite rainy place, comparable to Brussels, in which I spent quite a time.
Um, Actually, I think, yeah, so I was in Brussels. I didn't find it worse than Brussels, actually. Maybe it rains a bit more, but I think Brussels is a bit more overcast, maybe. So you get clouds sitting there for a long time. So yeah, in Durham, it tends to be, well, what we have in Durham is wind. So we have a lot of wind, but it means that the clouds get blown away. So yeah, the rain's not too bad there, not too much. It's actually one of the drier places in the UK, contrary to the myths.
Still, we have 1 minute, but we can maybe wait a couple of minutes.
Yeah,
we can wait a couple of minutes because people are always coming the last moment. By the way, Sravan, I just to tell you that I sent to the list of attendees of seminar information about the conference, and this somehow boosted the number of registrations.
Okay, good.
So I think it's okay. By the way, Irina, I also want to tell you that there is
I have to pass a registration, yes?
No, it's okay. About different thing. For this seminar, somehow this Russian email address, when I use it to send email to Russian people who registered, it doesn't show me to whom I sent and to whom not. It's a bit annoying, but maybe one day you can ask it there. Maybe I will send you exactly what I want to ask.
Write me a letter and I can call them on.
Because it's a bit annoying. I'm sending emails, they are not saved in a sent folder. It's like it's too much for me to remember what I did and what not about these emails. And
Okay, no problem. Yes,
it's not like a
I do myself. I ask my student.
And you, Sravan, you also missed the funny step of setting up a live streaming. I suggest you to join me next time.
Okay.
10 minutes before the
That's
talk.
the second time.
Well, I was in another talk here, so Shinji Mukoyama was giving a colloquium, and so I was.
Yeah.
That was finished, and then I rushed for this.
No, you see, it's really a practical thing. I really want to show you what to do because it's not always guaranteed to make it happen from China. If accessing Google from China is a little bit of trick, I can tell you.
Well, you can tell me some other time so I can practice it and I can do it next time for the next talk. Yeah.
Because the problem is if I turn on VPN, my Zoom is not stable. But if I turn off VPN, I cannot access Google. So I have to balance between these two things somehow.
You have to use two computers.
Well, I do differently, but anyway, it would be great if next time Sravan can do it.
Yeah, okay, yeah.
Because he is in a much better place from the point of view of Google.
Okay. Oh, sorry. What do you think? Maybe we can start now. Okay. Okay. Good evening, everybody, and good morning for some of you. Today we have a pleasure to have a Steve Abel talk. He will tell us about UV, infrared, ultraviolet, infrared mixing, effective field theories, hidden constellation, and origami, the Higgs mass, gauge coupling running, and naturalness from a string perspective. Please, 1 hour, Steve. And what do you prefer, that people interrupt you and ask you questions, or we can kindly ask everybody to keep questions to the end?
I prefer to be interrupted if people have questions as I'm going along. That's much better. Yeah.
Okay, thank you.
Yeah. So thank you very much for the invitation to speak and for the opportunity to speak. I do apologize for the long title. I couldn't decide what to talk about, so I thought I'll just talk about everything. So I didn't realize you would read out the whole thing, so I apologize. So I'm going to talk about this work with Keith Dines and also my student, Luca Nutricati. That we just completed a paper recently, and then we had a paper so a year and a half ago, and we're basically interested in a way it's a very old topic, so we're looking at closed string theory, but the thing we want to know about it is how does an effective field theory drop out of a closed string theory, and people have not spent very much time in the past working within a UV complete theory such as closed string theory in order to see how do I understand, for example, renormalization, renormalization group running in the full theory. So that's what we're about, and our motivation really is that we're hoping that when we do that, we'll find something that pops up that will inform us about questions and problems such as, for example, naturalness. So, you know, why is the Higgs mass much lighter than you expect it to be, and so on. So that's the thrust of the talk, and essentially the end result. Hopefully, you'll sort of understand a lot of the framework of it, but it'll sort of cast things in a slightly different light from what you're used to, thinking about. So let me just start with the motivation a bit more. So the thing that motivates us is naturalness. So why do we have such a light, for example, Higgs and standard model scales compared to, for example, the Planck scale? So one idea is that you should have some sort of way for the UV physics to talk to the infrared physics. So by infrared, I mean where the standard model lives. And so it's natural to explore that these two things should know about each other. So there's the first idea is UV IR mixing and associated symmetry. So we're interested in a picture generally. So if there was another one as well as string theory, we might be looking at that. But string theory is really the best one we have, where you have UV IR mixing and associated symmetries with it. Because UV IR mixing is probably going to involve physics at all scales, what you expect is that apparent symmetries that you have in the theory won't be apparent to low energy observers. So when you have a symmetry, UV-IR symmetry in the theory, it's something which to a low energy observer may give you, for example, a magical cancellation of parameters and operators which are much smaller than you would expect them to be. So you see, that's our motivation for why there could be something to do with the Higgs mass. So we're looking for finiteness through magic cancellations. And then if that's the case, then you expect also that, I mean, it's not mandatory, but UV-IR mixing tends to give you an infinite tower of states. So it's not just that I can have one scale and then another scale that talks to it. Sort of generic UV-IR mixing, including a symmetry, is likely to mix all of the scales together, and you can only really do that if you have an infinite tower of states. So that's the third aspect of this thing. And then finally, if you, for example, achieve finiteness, you're going to get some sort of conspiracy in order to make the whole thing finite. And the question is then, if I extract the effective field theory, am I going to see something in the effective field theory which is as a result of that? And also, how do I even extract an effective field theory from this sort of theory? So those are the sort of four generic ideas, and our motivation really is that we have a theory, string theory, where we can actually look at these things and see what happens. So that's why we turn to string theory, and it's really quite sort of, kind of common old garden textbook string theory we're going to look at. So closed string theory, heterotic string theory, if we're doing phenomenology, probably. So that's our starting point, really, is how do all of these things appear in string theory? And what we're going to do is we're going to return to string theory and try and look at how you understand these things in string theory by looking at specific items, the specific things that are giving us problems in the effective field theory. So those are mainly the Higgs mass, but also gauge coupling running can also be problematic. For example, if you have a large volume compactification, that's also problematic. So we're going to look at those two aspects within string theory, and we want to see how do you understand, for example, why the Higgs mass could be fine, it could be small. So that's our motivation. And one of the one of the things I'm going to start with is really this, well, what we call origami. If you're familiar with string theory, it's essentially the same thing as unfolding, but we like to give it a different name because we think it's the important aspect of UV-ion mixing, which is at work, so we want to sort of start from scratch, basically. So we're going to start just thinking about, well, origami. I'll tell you what that means, and then I'll talk about what that means in string theory, which is modular invariance. So that will be reviewish for quite a few of you, I think, but hopefully no one minds a bit of review. And then I'm going to talk about calculating the Higgs mass in this framework. And the way that we're going to have to do it is to do something which is equivalent to the Kalman-Weinberg potential in field theory. So in field theory, if you ask me what's the mass of a scalar or something, you don't have to tell me what the theory is. Any scalar theory is going to have something looking like the Kalman-Weinberg potential for the scalar in it. We want to find an equivalent for string theory. So when you have a string theory which is non-supersymmetric, what does its Higgs mass look like, or what does its potential look like? So that's what we want to talk about. And actually the techniques that we need for that go all the way back to, say, the 1930s. So they're sort of buried in number theory, Rankin-Selberg techniques and so on. So those are very traditional techniques in number theory, not so well known in string theory until more recently. And then finally, the most important thing really is how in that, well, is then to extract an effective field theory, for which we're going to have to understand how to do renormalization. And see, renormalization is going to be different from what you normally think about in effective field theory, because the theory is UV finite. So renormalization is really just then something you do in order to put an energy scale into the theory. We're not curing divergences apart from possibly infrared divergences if there are massless states, but there isn't this connection between, oh, a UV divergence means renormalization running. It's an entirely it's just a practical process for getting an energy scale into the theory. Then finally, I'll talk about naturalness with some sort of speculation about naturalness. So as I said, I'm going to start off with something with quite a elementary review of field theory and where UV-ion mixing comes into it, and origami. So if you are bored, I have the origami to make this frog here. So as you're recording this video, you can just freeze the video at this point and you can just make yourself a origami frog while I'm talking. Right. So let me talk about what I mean by origami to start with. So I'm going to go right back to just effective field theory. And as I said, we want to kind of look at the Kalman-Weinberg potential in effective field theory and do something similar in string theory. So starting with the Kalman-Weinberg potential, just to recall, so field theory 101 or something, 102 maybe, you write down, so a one loop potential, you write down all of the diagrams in the theory. You're interested in the potential, so you take all the external momenta to zero, and a lot of what I'm going to say is really for diagrams and amplitudes where external momenta are not important. So either you send them to zero, or if you talk about gauge coupling, it's just like a Lorentz tensor prefactor that you're not interested in. It's just the thing multiplying it. So, all right, so in this case, we send all the external momenta to zero, and what you're left with is an integral over the loop momentum. And it looks like a log, so it looks like this log. Because of symmetry factors, when you're summing these diagrams, there's a 1 over 2n factor, n is the number of vertices. So you get this log, you do the integral, and you get this, this contribution. I'm neglecting a quartic coupling, a quartic term. So so MUV is a cutoff. There's an MUV to the 4 term, which I'm going to ignore, and later on you'll see why I'm ignoring it. The first term, which is really talking to the Higgs field or the scalar in the story, is a quadratic divergence. So it's MUV squared times supertrace m squared, and then there's the m to the 4 term, which is if you like, the Kalman-Weinberg potential. So all of this is the Kalman-Weinberg potential. They argue that this leading quadratic piece is, you have to assume it's zero. And they work with the quartic piece there. So that was Kalman-Weinberg's, one of their contributions. And so the main thing is that we note we're supposed to put a cutoff into this thing, and you get this logarithmic running behavior and then the quadratic piece. So we want to sort of do the same thing in string theory, and the way to connect the string theory to this story is really if I take this story and write it in a world line formalism. So I'm going to take this integral and I'm just going to rewrite it using the Schwinger formalism. So the Schwinger formalism, the way it works is you introduce a Schwinger proper time and you calculate the amplitude for a particle to go from x to y within a time t, and then you integrate over all t. So in a sense, t is like the size, it's the length of the line, the length of the world line. And so if I look at this cosmological constant term, it's really just a mathematical identity. I would take the log here, and I can rewrite the log as this integral over a parameter t, 1 over t, e to the minus t, k squared plus m squared. So you can just check that does indeed give you a log. And so you end up with this expression. And the important thing about this expression is see where the MUV, I have to put that in there because it's divergent as t goes to 0. So it's got a UV divergence. The UV divergence is at t equals 0 in this integral. And so now to connect it with what we're going to do in string theory, I'm going to define this object to be the particle partition function. So it's -1 to the fermion number times by this weighting e to the minus t m squared times by 1 over t squared. And you see that object multiplies dt over t. So this is the sort of most stringy way to write the integral. And if you do this integral with this z in there, you'll see that you do indeed get the same potential as Kalman-Weinberg, so you get that potential. And then if I'm interested in the Higgs mass, I would take double phi derivative. And you see all the problems come from this term, really, because if this m, for example, is like a Yukawa fermion, it's proportional to phi, so m squared is phi squared, Yukawa coupling squared. Double derivative gives me something times by MUV squared, so I'm in trouble. It's big. So we'd like to understand, well, what happens in string theory with this particular thing. In field theory, you really just, you sort of mutter, okay, well, it's UV sensitive, so we have to think about the UV theory. No one ever actually does. No one ever actually calculates this thing in string theory as it is there. So that's what we're going to do. Right. Okay, so now let me just sort of render this into the most stringy way possible. So we have this integral. So this is our lambda, integral over t. and we got a function z, which I'm calling the partition function. So I'm going to draw it on a line like this, integral from 0 to infinity. And as I showed you, the t goes to 0 is the ultraviolet. That's where the ultraviolet divergence lives. T goes to infinity is the infrared. So in other words, if the states are massless, they would have a logarithmic divergence, coming from the logarithm. And that is at the t goes to infinity end of things. So now I'm going to head towards string theory. And the first thing I'm going to do, I'm going to define a dimensionless Schwinger parameter, and I'm going to call it tau2. And so tau2 is t over pi alpha primed. Alpha primed is something with dimensions of length squared, because t has got dimensions of length squared. And of course, you'll guess that this alpha primed is going to be the string alpha primed eventually. But anyway, at the moment, I'm just thinking of it as a way to rescale my Schwinger parameter. And I introduce a dummy variable, which I'm going to call tau1. And tau1, what I do is I integrate. So you see, this isn't doing anything really. This is just 1. d tau1 from -½ to 1/2 is 1. So you see, I've got this integral over this strip here. So this is the thing that looks most like the one-loop integral in string theory. So you'll see that eventually. But you see, one of the things that I can point out to you now is that if I want to regulate this thing and make it finite, I can put a cutoff on the infrared if there are massless states in order to make that end finite, and also on the ultraviolet. And those things are in principle independent cutoffs. So I have an independent UV and an independent IR cutoff. When I'm talking about renormalization, strictly speaking, what I should be talking about is the infrared cutoff. That's the thing which determines running and so on. This MUV is really, the way I think of it is that this cutoff, the ultraviolet, has nothing to do really with renormalization. It's just a divergence in the ultraviolet. Right, okay, so far this is just field theory rewritten. And now I'm going to suppose that there's an exact symmetry under tau2 goes to 1 over tau2. And ask, well, what happens if I do that? So it's not a field theory symmetry, but we can pursue it anyway. And in fact, I did in Babers de Luca at some point. And you can ask, well, what happens if I just do field theory on the world line with this world line symmetry, tau2 goes to 1 over tau2, what effect would it have? And so effectively, this becomes like a gauge symmetry. So what happens is my strip here, it gets two pieces, and there's a flip symmetry across the tau2 equals 1 line, which is a fixed point. And I have a redundancy of description. So what I can do is I can fold the S2 over into S1, and so it looks like that. So you see now what I've got rid of the ultraviolet divergence. I only have something which I'm interpreting as an infrared divergence. But in a way, because I've done this bit of origami, I've also lost, it's also not orientable. So I don't know if this infrared divergence is really an infrared one or is it an ultraviolet one. Likewise, I only have one cutoff I can put onto the theory, just the infrared cutoff in the way I've written it here. But I could also interpret it as an ultraviolet one. So you see, it's just putting this symmetry, which is a bit trivial, changes the way that you have to think about everything, the ultraviolet and the infrared. So, you can try and implement this symmetry. So let's see what happens if we do that. So you see, the strip is already invariant under tau2 goes to 1 over tau2, and the measure is already invariant. So tau2 goes to 1 over tau2, so it's d tau2 over tau2. So the measure is invariant. So the only thing that remains, if we wanted to make this a symmetry for this potential, is that we'd have to implement this symmetry. The partition function should be invariant under tau2 goes to 1 over tau2. And that is the crux of the matter. That's why it's quite difficult to just write down a theory like that, because it's quite hard to arrange a symmetry where the spectrum gives you a partition function with that symmetry. And so if you think about it for a while, you're sort of driven to think about functions like this, so an infinite tower of states. And so this is an example of a function that will do it. and the way that you show it is through Poisson resummation, which is basically, you take the function and then you write it as a Fourier transform of the same function, so Fourier transform, Fourier series. So so you get an identity between infinite sums like this, so that's called Poisson resummation. And if you have, in this case, a sum over an 8-dimensional integer lattice, these two functions are the same. But you see, from a field theory point of view, if I was to tell you the spectrum looks like that m squared is the sum over an infinite 8-dimensional lattice, you would just say it's a very tuned spectrum. It looks tuned until I tell you that it has to have this symmetry, and then there's no other choice, but it has to look like that or something like it. That's essentially what happens in string theory when you talk about one-loop diagrams in string theory. The spectrum in string theory is arranged in just such a way that you're going to get this sort of symmetry under mappings between, so tau2 goes to 1 over tau2 and so on. Right, so now let me turn to string theory. So have I got any questions at that point? That's a good time to ask questions.
Yeah, I mean, in the equation that you had before,
yeah,
do you have 1 over tau2 square in the exponential or not?
Oh, let me just have a look. Oh, sorry, this should be, yeah, sorry, you're right. This should be 1 over tau2, yeah. Sorry, you're right.
Yes.
There's a slash here. It's 1 over tau2.
Okay, thank you.
Yeah. Right. Okay. So now so you see, basically I've covered all of the physics you need. I just need to fill in the stringy bits, stringy details. So let me turn to the string one-loop diagram. The string one-loop diagram, and I'm going to talk about closed strings. So it maps out a torus. So it's really a 2-dimensional integral rather than a world line integral that we're going to be doing. And so the first thing that you can do is you can take the world, you can take this world sheet, which is a donut, and you can map it to the, you can map it onto the complex plane. And what you get is a rhombus, but the rhombus is defined by a single complex parameter tau instead of a single world line parameter t. And so because of the symmetry, the underlying conformal symmetries of the string, you have additional symmetries that you don't have in just the effective field theory. And one of them is tau goes to tau plus 1 and tau goes to minus 1 over tau. And you see that if you look at this rhombus here, the one which is defined by the tau, this tau there, it's the same lattice that you're going to get in the 2-dimensional plane that you've mapped it to, as if you had tau plus 1 here. See, just having a lattice made out of these rhombuses, the dark green one, is the same as having a lattice made out of the original tau rhombus. And the same if you do this transformation. What that does is it swaps and rotates the coordinates, but it's basically the same lattice that you get. And so you have to integrate over all of those things. And what you traditionally do is you define these two transformations, modular transformations, and call them S and T. S and T just redefine the lattice, the lattice of defining the torus. And you see that if I am integrating over all taus and I do S operations, if I, for example, begin at the very left here, I can do operations and get into this domain in the middle. Oh, I think I've got S and T the wrong way around here, sorry. T is tau goes to tau plus 1, and S is tau goes to minus 1 over tau. So the T transformations move you along one unit, and the S transformations do tau goes to 1 over tau. So you see that if I begin in this gray region here, I can get into that region if I'm below it, if I'm in this region here, by doing a tau goes to 1 over tau. So wherever I am in this region, I get mapped into the gray region. So anywhere in the tau plane, I can be mapped into this region. So you see that this fundamental domain we've got now is pretty much the shape of the tau2 goes to 1 over tau2 thing that I was talking about with this sort of toy symmetry. See, it's not that different, really. The physics is not that different. So now let me show you how the partition function looks to do the calculation. So we're going to have to integrate over all tau within that fundamental domain. And so let me give you a bit of notation. So the complex tau, I'm going to call tau1 plus I tau2. So tau2 is the imaginary part of that. So tau goes to -1 over tau is the same as tau2 goes to 1 over tau2. And also, just for notation's sake, I'm going to define something. Curly m squared is 1 over 4 pi alpha primed. Alpha primed is the string length squared. And so that's also the string mass squared on 4 pi squared. So wherever you see those things, they go between each other like that. Right, so now this is what lambda looks like. So as I said, it's an integral over the fundamental domain, which I'm going to call curly f, times by our partition function. And just like in the particle toy model case, this partition function has to be invariant under all of the modular transformations. And there's a theorem that any function which is modular invariant, I can write as what's called a Q expansion. So this is basically, you can think of it as a Fourier series, a complex Fourier series. And it's formed as a polynomial of these Qs. So Q is e to the 2 pi alpha tau. And so you can always write things in terms of this polynomial. And the reason that's useful is because when I'm doing my integral, once I get to the large tau2 part, so if I go back to the fundamental domain, when I get to this part, when I get to this part, which is the infrared, so tau2 is above 1, and when I integrate there, I'm doing tau1 right across. It projects to the states which have got little m equals little n, right? So it's a level matching, as it's called, projection. So I get approximately, when I go to large tau2, I get something that looks like this. And you see that looks exactly like what we had in the particle theory, right? So we just replace the world line parameter with tau2 in that region. And you see you get e to the minus pi tau2 alpha prime, which we identify as our Schwinger parameter, times by the mass squared. And those are the masses only of what we call the physical states. So that's the ones which have got m equals little n. So that's the level matched ones. And then you've got this coefficient, ANN. And these coefficients, all they're doing is just counting in the theory the number of bosons minus fermions at that level. That's all they're doing, right? So that's all sort of hidden there, or sort of contained in the partition function. All of that, all of the statistics essentially is sort of contained within these coefficients, these AMNs. So that's the way it looks. But you see now the problem, and what a lot of string phenomenology was all about, is how do I write down a partition function which has got these properties? Tau goes to tau plus 1, tau goes to -1 over tau, invariant. So that was sort of a big, at the end of the 1980s, it was a big triumph in string theory. String model building was to figure out how you can do that. And that's sort of one of the things that spurred really the first string revolution, I suppose. So we want to talk about models, about functions which have this property, but what I want to do, which is different from what was done all those years ago, is I don't want to start by telling you what this function is. I just want to talk about the properties of any function that has that symmetry. Right? So that's the thing I want to do, which is kind of what you would be doing in the effective field theory, like Kalman-Weinberg. No one asks you to write down the form of the partition function. It just gives you that Kalman-Weinberg potential. So it's mathematically quite complicated to write, just to get those properties, and in order to be able to do it, we're going to have to go back and think about these integrals in a slightly different way, using the techniques of Rankin and Selberg and number theory techniques, basically. So we want to say something general about what happens when we're doing this integral. So just to sort of warm you up for what the answer is going to look like, we can just look at the answer when I do that integral, the cosmological constant integral, and see how it can be written. And this is figured out by my esteemed collaborator Keith and also Kutasov and Seiberg, sort of in the mid-90s, really. And they found a different way to write this cosmological constant, which is that it's, instead of writing it as an integral of some function which is modular invariant, so like Jacobi theta functions or whatever, you can write the whole thing as a supertrace of m squared. So by supertrace, I mean you take the mass squared and you multiply it by -1 or +1 if it's boson fermion. So that's all I mean by supertrace. There is a question, of course, of regularization, because this is going to be an infinite thing. The tower of states is infinite, but if you'll accept that for a moment, it can be written like this: supertrace m squared. So it's a completely different way of writing the answer, and the supertrace is not over all of the states in the theory. It's only the physical states. So it's only the states with little m is equal to little n. So only the level matched states appear in the supertrace. So it looks like it's a very particle theory way of writing the answer, because it doesn't, there's no contribution where you don't have level matched states. It just looks like an infinite contribution from particle theories. It's like an infinite sum of particle theory contributions. But it's definitely not the normal field theory object. It's over an infinite tower of states. And so, if I just show you what's happening in terms of the spectrum, if I take, and we're talking about non-supersymmetric string theories, obviously, because if it's supersymmetric, everything is just zero anyway. So we're talking about what happens in a non-supersymmetric theory. You see that if I show you the spectrum explicitly of a non-supersymmetric theory, what it looks like, so I'm showing you the logarithm of those coefficients. So this is basically the number of bosons minus fermions at each level. And it's the logarithm of it, and then it's plus or minus times the sign. So I multiply with plus or minus if it's boson or fermion, basically. And so what you're seeing is that the spectrum oscillates, but it has no intention of ever going to zero when you go to larger and larger levels, energy levels. It's not looking like it converges at all. And just in terms of numbers, see, this is e to the 30. So these numbers are huge at each level, and it's actually growing because there's a Hagedorn growth in the spectrum. So it's got huge exponential growth. And yet, when you do the full sum, if you don't truncate it, you get a finite answer. So that's the sort of miracle of these sums, that you will, in the end, get a finite answer. And the reason why, just in terms of, if you just look at this thing, is that all of these multiplicities, they lie on a function which is smooth. So the function they lie on is smooth. So even though, from going from one level to the next, the numbers are completely crazily different. They're not looking like any kind of supersymmetric cancellation. Ultimately, they will cancel because you're summing them over this sort of envelope function. So that's what happens in the spectrum. So, okay, now let me show you how to derive it, or how you should derive it. I have to say the history of this is quite weird, because all of the techniques for this were developed, so Rankin-Selberg was 1939, 1940, and Zagier wrote a paper 1981, which specifically has to do with when these integrals are not rapidly decaying. So you have to do a bit more work in order to treat those things. Ultimately, that process is the same thing as is as subtracting logarithmic divergences if you're doing renormalization. So it's sort of bizarrely, all of the technology was there before string theory even came along, but string theorists never even noticed until maybe 10 years ago or something, but maybe 2010. Pialin and collaborators started to get into these things. And essentially the Rankin-Selberg side of this. But, before then, it was really just done sort of, people were only thinking within string theory and somehow managed to realize all of these things without using the technology of number theory. Anyway, so this is how you can do the same integral from a sort of number theoretic approach. And so what we want to do, we're given an integral like this, like that, over the fundamental domain. If I have an integral like that, the question is, can I write it in terms of only the level match states? So that's the states with equal numbers of left and right moving, little n equals little m. And so what you can, so the starting point is really to notice that if I take this partition function and I do the tau1 integral, so I integrate across the strip, wherever I am in tau2, I just integrate across the strip. It gives me a function which is level matched, so it'll give me a function which is a function only of tau2. So all of the tau1 dependence, I've just integrated over tau1. All that does is it projects the coefficient of q to the n to be the same as q bar to the m. Sorry, the exponent q to the n is the same as q bar to the n. So it's level matched. And so we want to write things, well, if we can write things in terms of this object, we've basically won. So then we've done our job. And let me show you how you can do it. So as I said, so this was invented in the 1939, 40. And then there were papers, also this one by Rabinovici from 2010, and these same three authors, where they kind of revisited Rankin and Selberg in this context. So this is how you can do it. And you can do this integral in 3 lines, basically. Do the integral in 3 lines. So this is how it works. Suppose I have it, so this f is the same as z. So we have a function we want to integrate over the fundamental domain. I'm calling it f here. You want to integrate this function over the fundamental domain. What you can do, you can take the function and I multiply it by an Eisenstein sum. So it's Eisenstein S. And the thing about Eisenstein S is it has a pole in S at S equals 1, which is a half. It's a half. And so what I can do is, if I can do this integral with the Eisenstein function in it, and I just take the pole of that integral at S equals 1 and multiply by 2, then I have my answer when there's no Eisenstein function in there. So that's another way to write my integral. So I'm writing it like that. 2 times the residue at S equals 1 of this object, right? So now this object is an integral over the fundamental domain. So it's an integral over that, but you can do an unfolding of that thing. So it's an integral over the critical strip. And what the unfolding means is that this Eisenstein series here becomes just what's called the seed. So it's basically, it's the Eisenstein, it's the bit of the Eisenstein function which is coming from the fundamental domain to the power s. And so what happens if you look at this side of things, you see this tau2 to the s. See, if I'm down here, if I'm down at this point, at this part, if I'm down below tau2 equals 1, I can map myself back to the fundamental domain by doing a modular transformation, and everything else is modular invariant apart from tau2 to the s, right? So tau2 to the s gets mapped back into the fundamental domain, and then I'm in some other domain, and I map back into the fundamental domain. By the time I've added all of those contributions up from the critical strip, I've got the Eisenstein series in the fundamental domain, right? So summing that thing over the critical strip by modular transforming back into the fundamental domain, it rebuilds this Eisenstein function here. So that's the way Rankin-Selberg works. And so this is an integral. You can just put this into Mathematica. G of tau2 is just this object. So you just put this object in there. You just put that thing into Mathematica, do the integral, and take the residue, and you indeed get 1/24 supertrace m squared. So the s equals 1 residue of that thing, of that object, is this thing, is that. So I'll leave that as an exercise for you to do. So that's the way Rankin-Selberg works, and it's really like a 3-line proof, really, once you've got that. So if you think about things that way, though, you get a different physical picture from what you normally think of. So normally, string theory 101, you're just working in the fundamental domain, and you just think about things in the fundamental domain. What happens if you do it the Rankin-Selberg way is you see that you basically, you have a contribution from an infinite number of cusps, right? So not only do you have a contribution from the cusp at infinity there, but you have a contribution from all of the other cusps at the bottom. Is there a question? Oh, okay. So you have a contribution from an infinite number of cusps. And like when we were doing the toy model, where I had a redundancy of a factor of 2, so I'd have to divide by 2. Here, there's an infinite redundancy. There's an infinite redundancy because I'm summing over all of these contributions, and that the effect of this redundancy, I have to divide by the volume of it. What it does is it takes what was previously a large divergence, and it turns it into what is at most a logarithmic one. And those logarithmic ones are infrared divergences. So that's the sort of amazing thing about Rankin-Selberg. What it manages to do by this, using this trick of writing things as the residue of this integral, residue s equals 1, is the residue is actually the thing that where you've divided out by the redundancy and the overcounting. Right. Okay. So now there's some interesting things that we can see that are happening also with this integral. If you think about it a different way, so the way that we did it is Rankin-Selberg, that it tells us what we have to do is you take the integral, you rewrite it like this. It's the residue at s equals 1, and this is basically just me rewriting the same thing. This is our little g, that d tau 1 thing. So this is a Mellin transform, and there's an inverse Mellin transform which tells you that this object is actually pi over 3 times that residue. So the pi over 3 comes from the Riemann zeta functions that were in there. So I'll just explicitly put in s equals 1 there. So pi over 3 times the limit as tau 2 goes to 0 of this function g. And so let me just remind you what g was. It was the integral across the strip of the partition function, which looked like that. So our answer, so the integral is pi over 3 times the limit as tau 2 goes to 0 of that thing. So now this is the thing. And you see that in 4 dimensions, at least, this partition function, it begins 1 over tau 2 times by supertrace. And so it looks like it should diverge, this limit. It looks like it should diverge, and it doesn't. And so one thing that you can say straight away is if I just Taylor expand this thing, the first term is 1. So it tells us that supertrace 1 is 0 in these theories, because otherwise, if it were not, then this thing would diverge because there's 1 over tau 2. So this is another way to understand that this is giving us a finite result, is that if you take that integral across the critical strip and you take tau 2 goes to 0, something which looks like it should be infinite and divergent is actually a constant. So in other words, the leading contribution, supertrace 1 over tau 2, supertrace 1 is equal to 0, even though the theory is not supersymmetric. So this is sort of one little miracle which is already there. Supertrace 1 equals 0, despite the fact there's no supersymmetry. And it's nothing to do with supersymmetry. The spectrum is completely non-supersymmetric. Sometimes people also say it's behaving like a 2-dimensional theory in the UV. And I think maybe Seiberg and Kutasov put it like that. The reason they say that is that this prefactor, which appears in the partition function, depends on the dimensionality. And if it's 2-dimensional, this is just a constant. So you can write it that way. I think it sounds a bit less miraculous than to say supertrace 1 equals 0. One thing you should also note is that when I say supertrace, you see that because we're taking the limit as tau2 goes to 0, we have a definition of what we really mean by supertrace when it's an infinite tower. It's if I'm taking supertrace of something, x, it's actually this object. So I'm taking a sum over everything, the physical states, but I put in e to the minus ym squared and take the limit as y goes to 0. See, that's basically what's happening when you do that. Right, okay, so I need to speed up a little bit, I think. So I think the supertrace 1 equals 0 is just one example of a magic cancellation, and we believe that there are many more in the theory that will pop up. So for example, if there's any operator, if I do any integral of an operator which is multiplying, it kind of appears as a summand in the partition functions. Take any operator which is tau2 independent. I stick it in this sum. So it could be, for example, charges or something, depending on charges. As long as that thing is modular invariant, the supertrace of it will be 0 for the exact same reason that supertrace 1 is 0 for the partition function. See, the partition function trivially just has x equals 1 there. But it would be true for any x. So supertrace of any x is 0. And, you know, likewise, if I do the Rankin-Selberg, the integral of that thing is going to be 1 over 12, well, curly m squared. So curly m squared is the reduced stringma times by this supertrace. Right? So for the partition, for the cosmodular constant, it was supertrace m squared. Now it's just supertrace x times m squared. So, you know, there can be more magic cancellations, essentially. Right, so hopefully you've got a flavor of what happens in normal closed string theory from a Rankin-Selberg perspective. So from a number theoretical perspective, what is happening with the spectrum and all of the states in order to make everything finite. Right, so now let me turn to the Higgs mass in the last, I think I've got 10 minutes left. So I'm just going to talk about the Higgs mass. So what does this mean for something like, if we want to talk about something like the Kalman-Weinberg potential? So now it's we kind of have a string, it's a string phenomenology question, but it's very different from what is normally done in string phenomenology. So normally string phenomenology works, you know, as follows. You start, you invent a vacuum, you build a string model, you look at the massless states, you construct a Lagrangian from the things which are massless or light. And then what you do is you throw away the ultraviolet and you just talk in terms of the effective field theory. What we want to do is really ask, how do we get the effective field theory from what is essentially going to be a big mess? The spectrum is a big mess. Right, okay, so now, as I said, so let me just emphasize this one. We don't want to establish a particular model for the Higgs mass. We want to just establish an equivalent to the Kalman-Weinberg potential. So it's a modular invariant framework to operate within the full theory, which is going to remain UV finite. All right, so we're interested in m squared. Let me just sort of give you a flavor of how it works to speed up a little bit. What we're interested in, you know, just like the normal Kalman-Weinberg potential, is if I take the infinite spectrum, what I want in order to calculate the Higgs mass of that thing is basically I need the Higgs dependence of every state in the spectrum. And so I have a left moving set of states and a right moving set of states. They all depend in principle on the scalar, which I'm calling the Higgs. So what I'm talking about is true for any scalar, but suppose let me just call it a Higgs for the sake of argument. So basically the entire spectrum will shift. But one thing that is certainly true is that I'm not allowed to shift the left moving modes differently from the right moving modes, because you can see, you know, the way that everything's arranged. If I think of the way the Q expansion works, if I do a tau goes to tau plus 1 shift, modular transformation, all that does is it shifts everything by either m left squared or m right squared, depending on whether it's the q term or the q bar term. And those things have to shift the same, otherwise something which was physical would become unphysical. So that is the main constraint that we have. And so it means that when we take our partition function and we want to calculate the Higgs mass squared, which is a double derivative of the cosmodule constant, I'm thinking of it as, what I can do is I can just operate with, by taking a double derivative on these exponents there. So that's the thing which comes into the integral from the Q expansion. And then the important point is that there's no dependence on the difference in the left moving modes and the right moving modes. Everything just depends on the sum, which is m left squared plus m right squared. So in other words, my summand, so the thing that goes into there, is going to be this thing. So that's just taking the double derivative. Oops, not that thing, this thing, x at the bottom. It's the double derivative of those exponentials with respect to phi. So that's what I get. It's almost there, but not quite, because if I do that, this summand is not modular invariant. So those derivatives, d by d phi, are not modular invariant ones. So one thing that you have to do is you have to shift this summand by a constant, and the constant depends on the particle content of the theory. So it's like it depends on a Casimir trace, essentially. It just depends on the gauge content of the theory, or what the Higgs couples do, essentially. So you get an additional cosmological constant contribution due to this modular anomaly of just the X part. And so when people have thought about this in the past, and they were looking at one loop contributions in string theory, you do actually find these things, but from different arguments. So there are other arguments which show you what this should be. Normally, you interpret it as a Higgs-dependent back reaction on the compactification. So it's just a gravitational effect, essentially. Anyway, right, so now if we put this into Rankin-Selberg and do our operations, what we get, so we get this term. So you see that this constant, the psi, this one, that's multiplying just the partition function. So, and it's a constant. So basically that just gives us lambda. So we get a connection between every scalar mass squared will get a contribution proportional to the cosmological constant, regardless of what the theory is. So even today, in effect, if you believe closed string theory is relevant today, then that should still be true, that the Higgs mass squared will have a contribution from the cosmological constant, depending on this parameter psi there. Then you get the second term, and this term is basically the double derivative of the lambda, which we already saw. So that is something which you'd not be surprised at. And then what you get is something which is either infinite if the state is massless, or zero if it's massive. And the reason why is that so far, all we have in the theory is logarithmic divergences or states which are massive. Logarithmic divergences now from states which are massless. So that is the same as you would have in field theory. We haven't yet regulated the theory, and also it doesn't know anything about energy scales. All it knows is it has the spectrum. But if I put a state in and I say that the state is massless, it doesn't know how to make that thing finite. It's just going to give me a logarithmic divergence, And likewise, if it's massive, and so it won't have a logarithmic divergence, it doesn't know how small it has to be, so it will just make it zero. So that what I have to do is I have to put in some notion of energy scale. So this is where we have to talk about renormalization. So let me just sort of summarize this very quickly. What we want in order to put in a renormalization scale is some infrared cutoff. So if I'm thinking of the fundamental domain, it means I have to put into the integral some cutoff which will remove the light states from the integral. And those light states, I interpret those as being part of the effective theory. So they're not contributing to whatever's making my coupling size, whatever it is. I'm not integrating those things out. They're in the effective theory. So that's the interpretation of this cutoff. The tricky thing is that this cutoff, when I do this, has to be itself modular invariant. And so we take our integral, any integral, and modular integral, and if it's an integral of some function f, which for lambda would have been the partition function, we have to put in some other function which has this property that it wants to crush things in the infrared, and it wants to leave things untouched in the ultraviolet. And so that was the sort of one of the main advances we were able to do. We have these properties we want, so the function should be modular invariant, should look roughly like this. So when tau2 goes to 0, it's 1. When it goes to infinity, it's 0. And then there's another property that we'd like, which is that the tau2, we're putting a cutoff on tau2 on this integral, and we're interpreting it as the energy scale. But it doesn't make sense to do that unless you have a symmetry under tau2, under this scale goes to 1 over the scale, because tau2 is just a world sheet parameter. So there should be an invariance under tau2 star goes to 1 over tau2 star. Otherwise, we're favoring one fundamental domain over some of the other ones. So, in terms of the critical strip, we want to have the same cutoff on all of the cusps, just not just the fundamental domain one, but all of the other cusps have to have the same cutoff in order to be able to do the whole Rankin-Selberg procedure. And so there's this symmetry. This symmetry translates into a symmetry under the function going, which is a function of cutoff, mu, goes to m string squared over mu. So it has to have that symmetry as well. All right, so I don't have time to tell you about which function we chose, but there is one, and we adapted something by Karitsis and Kunas. We had to adapt it in order to get this last property, in order to get that property, which is basically, you can think of it as it's a kind of agnostic to which fundamental domain I'm talking about. All the cusps should be equivalent. That is the only thing which can be consistent with Rankin-Selberg, because, Rankin-Selberg, remember, all of the cusps contribute. If I don't have this symmetry, it will mean that some of the cusps are contributing more than other ones, which wouldn't make sense. So I don't want to favor any cusps. Right, so now let me give you the answer. So what's the answer we get? So this is our final mass squared. It looks like a cosmological constant plus the double derivative of this, what we can call a regulated cosmological constant. And if you look at that thing, you'll see that this has the same form as Kalman-Weinberg, as a Kalman-Weinberg potential. However, in order to get this, what you start with, after you use this cutoff function, is an infinite sum of Bessel function. So you have quite a job in order to extract this logarithmic running term. And also, in order to see that, what's contributing here are, only masses which are less than mu. In other words, what you would call your effective theory. And then this part, it's contributing this second supertrace term is all of the masses which are greater than mu, so the ones you've integrated out effectively. But so you see, you have a kind of running Kalman-Weinberg potential, because, once mu falls below the mass of a state, it will disappear from this expression once mu falls below. Once mu falls below the mass of a state, the state is heavy effectively. It won't appear in the logarithm. And the C's here are just really some parameters which are sort of free to choose depending on how you define the partition, the cutoff function. So this regulator function that we're using, the G hat, has some freedom in it. And so that is some freedom in order to choose different constants here. Right, so this is what the picture looks like for the Higgs. And so let me begin in the infrared here. So if you have a theory which has got no massless states, what you will have in the infrared, you will inevitably run to a Higgs mass squared, which is the same as if you'd just done the integral with no regulator. So if there's no massless states, there are no log divergences. I could have just done the one loop integral for the mass squared, which would just be the double derivative of lambda of the cosmological constant with respect to the Higgs. And that's where you're bound to end up. Wherever you start from, wherever you start from, you must end up there. What happens if you have massless states is that there are some logs which never go away. So you would then end up with something where there's an effective field theory description in the infrared, which has got the same infrared divergences as the particle one. As you increase the energy scale, so as you increase mu, what happens is that the mu will get heavier than some states. Those states will start to contribute to the effective theory, and it will then start running. So you'll get logarithmic running or power law running, depending on the setup that you have in this region. And there it will just look like the effective field theory that you expect in that region. So all of that continues until I get to the string scale. So once my regulator function, the cutoff, approaches the string scale, it has to turn over because it's got mu goes to 1 over mu symmetry. And then it will just reverse on this side. So it has to go down and just reflects around mu equals m string. So that's the final sort of picture of running for the Higgs mass squared. And you see that, so one thing you notice, if you're used to, for example, functional renormalization group or exact renormalization group, the way that you normally think of it is that there's a sort of bare action and then there's an effective action. And you normally think of the theory running from something in the deep ultraviolet, which is the bare action. And then, in the infrared, you get to something else, which is the effective action. You see here, they're actually the same. So if I crank mu up to infinity, I just end up in a kind of reflected infrared. So this here, you can think of this end of things as being kind of like your bare action. There is no real bare action. If you insist on looking for one, it's just another infrared. Right, you can do the same thing with gauge coupling. So this is the final slide almost. So with gauge couplings, you see that what can happen there. So this is, I'm comparing it to a famous result of Dixon, Kaplanowski, and Lewis. So this is for people who are familiar with that result, essentially. So Dixon, Kaplanowski, and Lewis talked about 2 toroidal dimension compactifications. You have a threshold correction in those theories that they calculated, which depends on the moduli of the 2 toroidal dimensions. The moduli are T2 and U2. And so those things, they're also modular functions. So these are Dedekind eta functions that are appearing there. This is the whole expression. So you see what the infinite tower of Bessel functions looks like. So it's a bit of a mess. But then if you go to the infrared, so far below the string scale, it ends up looking like that. So this is one contribution to the contribution that Dixon et al. Looked at. So you see, you get their threshold correction plus log running. And so it does this sort of behavior that, similar sort of thing. You go to an infrared fixed point if there are no massless states. As you increase the energy scale, you'll start to get log running. And then you get 6-dimensional behavior, at which point it goes flat. And it actually doesn't run at all in the 6-dimensional regime. Right, okay, so now let me just go to the conclusions because we're running over time. So thank you very much for your attention. So I've been talking mainly, so one of the takeaway messages really is that what we've developed is a way to get Kalman-Weinberg potential in a completely model agnostic way for modular invariant theories, which doesn't require you to do any kind of ultraviolet. I mean, it remains ultraviolet complete, but it has a Kalman-Weinberg form. So we understand how the EFT emerges from the theory and how to do renormalization group running and so on. And so, for example, you can start with that, and you know, you can develop things like a stringy hierarchy condition and so on. But hopefully, ultimately, then you start to understand things that may explain hierarchy problems. You can think of it as a kind of solution to the technical hierarchy problem, in the sense that if I give you a theory where it's got cancellations, whatever running happens, once you run up for the infrared, it doesn't really affect what the infrared answer is. So the infrared answer is the kind of unregulated integral. Running is something that appears when you go into the high energy regime. Right, and then so this is the final thing, that none of these relations have it. It's all non-supersymmetric that we're talking about, and it's really just to do with modular invariance and UV-IR mixing. Right, okay, I'll leave it there. Thank you.
Okay. Thank you very much for your very interesting talk. Questions, please. I don't see any questions. Alexei, please ask your question.
Yeah, maybe I will ask some question. Thank you, Steve, for your nice presentation. I'm, how to say this better? I'm a little bit confused because I understand what you are saying. I also tried to understand this when we were recombining in CERN and we were discussing naturalness of all of this and UV-IR mixing. And I think I barely understand the procedure which you explain. How do you suppose to join whatever you discuss here with some other results which we know about, positivity bounds, unitarity bounds, which we obtain in series without applying to some UV-IR mixing or stuff like this?
Okay.
Do you see this? Do you see reflection of this somehow in your?
Yeah. So actually, so the positivity band. All I can say is it's a very interesting project. Would be to see if I take this procedure and I look at the positivity bounds, using it in these sorts of theories, whether there's something which has to come in and fix up the ultraviolet of those theories. Because, yeah, according to those, according to that problem, that the positivity bound problem should go away, really, or there shouldn't be a problem here. So how? Yeah, so I don't know is the answer, but it would be an interesting problem. Yeah, so yeah, so I mean, I did ask the people who do positivity bands, but I didn't. I think they haven't thought of doing it within a UV complete framework, but I think it would be a natural thing to think about, really.
Yeah, because this is actually very intriguing. I agree with you that in your approach, positivity bounds themselves should go away.
Yeah.
But apparently, in our canonical, let's say, point of view, we obtain this positivity bound. So it would be very curious to see how do they really go away, what really makes them to not be so much important. But which is much more intriguing is, I would say, unitarity bounds, which are recently discussed by people. Unitarity bounds also. By the way, it's also would be my second question maybe here. Is it obvious that all your construction which you explain is obligatory unitary?
It's as unitary as string theory is unitary, essentially. Yeah. I mean, so I can't prove it to you, but yes, we hope it is essentially. That's yeah. So in that, yeah. So then we're no different from just what people normally do in string theory, but so we don't have anything more to say than traditional string theorists on that. Yeah, with the thing with the unitarity bound, with the positivity bound, which makes it a little bit different from what I was talking, is there you need to keep track of momenta. So I would have to make I would have to construct diagrams which have got where I'm not just setting momenta to 0. But maybe you could probably handle them in well, hopefully in a fairly straightforward way. I think you could probably handle them fairly straightforward.
I see. Yeah, it would be curious to see how is it going to be a straightforward way.
Yeah, I mean, well, so for example, if I'm doing the gauge coupling running, some things, you can just remove some factors because they're Lorentz tensors or something like that.
I see.
So possibly from the structure of those diagrams, you can kind of simplify the things a little bit. But it did look quite hard to do it, I have to say.
Okay.
Yeah. I did think about it, but I mean, not super deeply, but I thought about it enough to realize it was quite hard.
I see. Okay, thank you.
Yes, Dimitru, please ask your question.
Oops. Hi, Steve. Nice
Hi.
talk. Thanks a lot. I really enjoyed it. It reminds me of some work I did myself too. First, pretty much everything here is heterotic string. I suppose you don't talk.
Well,
it could be or anything else because you don't have modular invariance. And field theory with tadpole cancellations would be fun to do, perhaps. But
right, yeah. So
I mean,
yeah, so this applies to any closed string theory. So it would be type 2b, but also it should also apply to the closed string sectors of open string theories, So
right. Then you have to patch up with some tadpole.
Yeah, then for the open string sectors, there would be something different operating, so like tadpole cancellation or something.
Right.
So for example, the equivalent of the supertrace 1 equals 0 thing would probably be a tadpole cancellation or something.
Now I have a question which is slightly related to the previous one regarding unitarity. Because here you're concentrating on the scalar potential, if we talk about the Higgs, or for the gauge couplings to the on-shell 2-point function.
Yeah.
Now, of course, at some point you have to go off-shell, because also for the Higgs, you have to do the Higgs running from 0 momentum to some value of the momentum, because you want to, the theory is clearly non-renormalized. So I play this game on effective field theory or defaults. Obviously, if you even on field theory grounds, if you can play the game to impose modular invariance without caring about string theory, right? But in that case, if you did for 2-point function for the Higgs, let's say off shell, what happens always, you get higher derivative counterterms. So you get, for example, for the Higgs, you get H dagger box H in superfields, or if you want, in scalar in components would be Higgs box squared Higgs.
Yeah.
So which means there is a pole, maybe a ghost, and then you have a host of complications. So what I'm trying to say is that you don't really solve naturalness in a sense, because if the compactification scale is high, it's one problem. If it's low, then the high derivative counterterms are suppressed by the large radius, are not suppressed because you have a large radius, so they get enhanced. That contribution is large. So you have to play a game. You are in between. Is there high compactification or low compactification scale? You have a problem, because if it's high compactification scale, you would have some sensitivity to that scale. And that's not nice. If you want low compactification scales, that's good, but you end up with momentum to power 4 times r squared, let's say, where r is some radius. And it's another problem there. Apart from the fact that you have this extra pole, which I haven't looked in detail what it brings. So, well, I fully agree that first thing is to look at the scalar potential and the one-loop calculation. because this is a higher dimensional series. You really have to go off shell and compute the 2-point function for the Higgs, the additional corrections from there,
right,
to a definite function. I did that on field theory grounds. I don't know if you can simply say, oh, I want to impose modular symmetry and play the same tricks that you did here, but for the off-shell part, for the running of the Higgs from 0 to its pole mass.
Right. Yeah. So what I would hope, although I don't, so it's a very, very interesting question, but I'm going to try and answer it. So what I would hope is that, so in the end, the picture is that you should basically think of expanding around the infrared. That you put it, you have an integral which is unregulated, and in order to get a scale into the thing, you have to regulate it, and in regulating it, you come away from the infrared. And so I would hope that those corrections are sort of under control as you're coming from the infrared sort of upwards. But yeah, I can't tell you straight away if they're all under control or not.
You see, we have this problem also for gauge coupling. Perhaps this is more familiar. It's exactly the same issue. So you do the off-shell 2-point function for the photon, the additional corrections, because first you do it for on-shell. So, okay, you get these results that you mentioned. But then if you really want to do the full running of the gauge couplings, you really have to go off-shell.
Right.
So you really have to input. And what you get, even heterotic string we're talking here, if you want to match to that, you get higher derivative counter terms like W box W, where W is a supersymmetric field strength. And that gives you F box F, where F mu nu box F mu nu, where F mu nu is the field strength of the gauge boson of the photon. And again, that part comes multiplied with some volume of compactification. And again, you have additional pole there, and that part is being missed. Again, would be interesting to, perhaps it's simpler that to implement there a modular invariant regulator for that piece of the one loop calculation.
Oh, okay. But this volume term, is it not the same problem as the normal volume term problem that you would have if I have a large compactification volume? It's not worse, presumably, than that. It's just an additional.
Well, it is a high derivative counter term. So what I'm trying to say is that whether Higgs or gauge couplings, you always have a high derivative counter terms, because everything is an expansion. Thinking of field theory grounds, everything is an expansion which comes multiplied with powers of compactification scale, because that's the only physical scale from the 4-dimensional observers, right? We have only the radius. So corrections would go either like 1 over radius or like powers of radius. So if they go like powers of radius, would come multiplied by the momentum.
Right.
So, and that part may be, we can discuss that privately, but that part of the running of gauge coupling from 0 in terms of the momentum would be really interesting to do.
Okay. Yeah. So, so one comment is that, there is another scale which could appear, which is the string scale itself, which could appear in the denominator there, maybe. But I don't know. I don't know if it'll appear there or not.
For the gauge coupling, I did that calculation. You only get volume of compactifications times this operator, W box W.
Right.
And for the Higgs mass, again, you get 1 over R squared, that's leading loop correction, but then everything is R squared times, again, higher derivative.
Right.
So, and this is expected because the 4-dimensional observers only knows about the radius of compactification, doesn't know what the string scale is or whatever, right? You do the loop calculation, the off-shell Green function calculation as a loop level, and you only have a radius of compactification, and that's it, and the momentum running. And what I'm saying is that you always have you were concerned more with the physical scale dependence on for the gauge coupling, let's say, which is 1 over R squared, like Dixon coupling scale with extra correction that you mentioned.
Right. Yeah.
But you really have additional momentum running, which you have to take into account. And that means you have to compute these higher derivative counterterms. Right. And of course, you can do that in string theory, right? We discussed, and you know how to do that. And this higher derivative, the coefficient of this higher derivative counterterm in string theory, you can tell me what that is.
Yeah.
Probably.
Yeah. Easy. So I mean, you're right that if you're so you're right that if I'm coming from the infrared, I don't know anything about the string scale at all, and everything will just be a radius dependent thing. The thing which is the thing which is different here is that in addition to that, there'll be contributions which could be finite on top of it. Those are typically coming from like relevant operators or something, which those are sensitive to the UV and they'll just give you a constant or something. But all of the running is kind of just going to be radius dependent thing. Yeah, so I think you're probably right. I think it will just be a radius dependent behavior that will probably be similar to the field theory one. Okay.
Actually, having just agreed on that, now I have second thoughts, because if you somehow manage to, let's say we go beyond field theory and do exactly what we discussed, but using a modular invariant regulator on the field theory side, maybe it's not just like 1 over R dependence and R dependence, but it's a modular invariant function of R.
Oh, you probably will get something like that. I mean, it'll be like, kind of like the Dixon-Kaplanowski-Lewis result, right. Because, I mean, the reason you get the Dedic and eta functions of T and U is because...
it's modular invariant.
Yeah, it's reflecting the modular invariance of the actual function it's starting. So I think you will get something which is modular invariant. I don't know if that will help you solve with those operators.
But again, it would be really interesting if you really tried for the gauge couplings alone, because it's easier than for the Higgs. Just the higher derivative 2-point green function of shell.
Yeah.
You go to 3-point function and cut one leg and mimic somehow a 2-point green function of shell on a string calculation and compute the coefficient of that operator, because that's crucial for field theory. On field theory side, you don't know what that is, right? It would be a counter term with an unknown coupling. But on string side, you can compute that coefficient, and you tell me it's pi squared over 3 or something.
Yeah.
And that would be really interesting.
Right. Yeah.
Okay. Thanks a lot. I enjoyed your talk.
Okay.
Thank you.
Maybe we can discuss further.
Yeah.
Okay. I see one more question. The question from Huang Wu. Please ask your question, Huang.
Okay. I have first of all thank your presentation. My question is why in your picture about UV and IR, why there is two IR?
Okay.
Two IR.
Yeah.
What means?
Yeah. Oh, so it really comes from this. When we define our mu, when we're imposing this regulator function, so we add this regulator function. Yeah. So the regulator function, it puts a cutoff into the integral, and where the cutoff is defining our mu scale. But the thing is that the cutoff in the regulator function, the regulator is a modular invariant function itself, and it's not only putting a cutoff there, but it will be putting a cutoff on all of the other cusps. On all of the cusps there'll be a cutoff because it's modular invariant. And then what we have to insist is actually none of the cusps is preferred. They all contribute the same because they're all contributing to the integral. So if we don't make them all the same, it's going to be a weird like some of them are contributing more than other ones. So we want to have a kind of democratic contribution from all of the cusps. And so because of that, we have to make sure that you've got this symmetry with the modular invariant symmetry, which means that you've got this mu goes to M string squared over mu. That's what it translates into. So, you know, I'm basically doing symmetry under that goes to 1 over that, which is mu goes to M string squared over mu, it turns into. And so, yeah, the answer is then it has to be symmetric under mu goes to M string squared over mu, which is this reflection symmetry. So you can ask what it means physically. You know, if I'm living down here, if I'm living in the deep infrared on one end, and then I want to ask, well, if I take mu to infinity and I see that things are changing, you know, what are the degrees of freedom over here which are changing, you know, in order to make this effective coupling come down again? There in that regime, you're probably talking about winding modes or some large long string modes which are interacting with each other. From the perspective of the degrees of freedom on that end, you know. So I think there will be a way of describing physics at this end, which is going to give me a gauge coupling which reverses, but it won't look like a field theory. It'll be something with like long string interactions or something.
Okay. More questions, please? I do not see any question. Let's thank Steve once again for his very interesting talk. Thank you very much. Thank you.
Thank you.
Thank you,
Thank you, Steve.
And bye-bye.
Okay, bye.
It would be great if you will send your slides.
Oh, okay. Yes, I'll do that.
I should find time to upload a lot of them to our website.
Okay.
See you, Steve. Thank you very much.
Okay, thanks a lot.
Bye.
Bye.
Yeah.
Bye, everyone.